This is a learning experience about water quality and fish kills. We will discuss how these things are related to each other throughout this lesson. First, let's discuss water quality. The term water quality can refer to the chemical, physical, and biological properties of water. The most common measures of a water's physical attributes are temperature, turbidity, conductivity, total dissolved solids, total suspended solids. Chemically speaking, water quality can be gauged by pH, dissolved oxygen, nitrates, and phosphates. And finally, a common biological test that is often performed on a water sample is known as E. coli. Let's start by learning what pH is. pH is a very important measure and is always taken on a water sample. In short, pH is a measure of acidity or alkalinity. The water molecule H2O is always broken up into H plus ions and OH minus ions. When water has a low pH, that is to say less than 7, there are more H plus ions present. This can be described with the term acidic. Neutral waters, or pH of equal to 7, have the same amount of H plus ions as they do OH minus ions. Water is rarely perfectly neutral and is almost always either acidic or basic. Basic or alkaline waters have more OH minus ions than they do H plus ions and is described by a pH of greater than 7. Fish and other aquatic life can live in waters with a pH of 6.5 to 8. Anything out of this range can be harmful to the aquatic flora and fauna. So what causes this change in pH? Is it natural or is it caused by human pollution? Well, both actually. pH can change naturally through photosynthesis and respiration. In photosynthesis, CO2 is removed from the water, which causes an increase in pH. So when rates of algal photosynthesis are high, for example during daylight hours and growing season, the pH increases. In contrast, respiration of living organisms and decomposition processes produce CO2, which dissolves in water as carbonic acid, thereby lowering the pH. In areas of excess air pollution, like elevated emissions from industrial sources or coal-fired power plants, or where water bodies are poorly buffered, like in high-altitude streams or low geological sources of limestone, acid precipitation can seriously impair the aquatic biota. Even in our region, in southeast Ohio, acid mine drainage from past mining of high-sulfur coal impairs thousands of kilometers of streams. While pH is considered a chemical property of water, turbidity is considered a physical property of water. Turbidity is a measure of the cloudiness of water. It can be estimated by measuring the intensity of a beam of light that is shining through a water sample. It is often recorded in NTUs, or nephelmetric turbidity units. A normal range of NTUs is 1 to 10, 1 being very clear, like that sample on the left down there, and 10 being rather muddy, like the sample on the right. Now, muddy water might not seem like a big issue, but it can actually be detrimental to a stream's health. For one, it can reduce the growth of aquatic plants by blocking sunlight, and it can also increase water temperature because suspended particles tend to absorb more heat, just like if you're wearing a dark shirt on a sunny day compared to wearing a light shirt on a sunny day. The dark one will get hotter because it absorbs more light and therefore more heat. The temperature increase on the water can actually cause the solubility of oxygen to go down, which decreases the dissolved oxygen levels in the water, which fish use to breathe. This domino-like effect on the water can be quite alarming, and that's without even mentioning the physiological stress put on the fish due to the coating of their gills, integument, and mouth parts. How would you like to live in a cloud of dust like that fish shown there? Turbidity usually increases dramatically after rain and storm events, as more soil particles are eroded from banks and washed into the stream. Exposed banks, bare soil from agriculture or construction, insufficient vegetation, urban runoff, and excessive algal growth from nutrient enrichment are all contributors to water turbidity. Another very important chemical quality of water is dissolved oxygen. Believe it or not, fish and other aquatic species actually need oxygen for survival, just as us land animals need it. As we said earlier, oxygen is more soluble in cold water than it is in warm water. That is to say, it dissolves easier in cold waters. A normal range of dissolved oxygen is 2 to 14 milligrams per liter. Some fish have no problem living in the lower end of that spectrum, but other fish are more sensitive to it. For example, trout and salmon. That's why they tend to live in colder waters. There are a few different reasons that a water source would have low dissolved oxygen. For one, high water temperature. Oxygen gets less soluble as temperature goes up, and the same is true for CO2. That's why cold soda pop tends to be fizzier for longer than warm soda pop. Another reason is the respiration of aquatic animals. Again, fish need oxygen just like us, so if there's a lot of fish using up a lot of oxygen, it's going to have lower levels. Another reason a water would have low dissolved oxygen is the decomposition of organic matter. If there's a lot of algae that ends up naturally dying, the decaying process can use up a lot of oxygen. Same goes for wastewater treatment plants. They tend to discharge a lot of organic matter that is still in the process of decaying. So we've just learned that dissolved oxygen is an important asset to any water source. We've also learned that too much algae can diminish a water supply's dissolved oxygen. But how would an algal bloom get so out of control that it would actually compromise oxygen levels of the water? Well, one contributor to this is the nutrient known as nitrate. Plants and animals use nitrate for growth. But as the saying goes, too much of a good thing can be a bad thing. Excessive nitrate can expedite a process known as eutrophication. See, when plants such as algae have too much food, they grow a ton. This explosive growth of algae can reduce levels of light in the water column, causing plants and algae to die. As they decay, the microbial activity associated with decomposition depletes dissolved oxygen. It takes oxygen out of the water. The lower DO can be harmful to the fish, as we've discussed, and other aquatic life. This can sometimes cause massive die-offs, known as summer kills. These extra nitrates can be a result of a number of different things. Mainly comes from runoff of agricultural land that has experienced excessive use of fertilizer. It can also come from wastewater runoff, failing septic systems, or even from animal feedlots. Like nitrogen, phosphorus is an essential nutrient for plant and animal life. In most freshwater systems, phosphorus is a limiting nutrient. That is to say that it is so valuable, most of it is taken up right away by living organisms that need it for growth. Thus, even small increases in phosphorus can promote rapid growth in algae, which can result in low dissolved oxygen and the death of fish and macroinvertebrates. Phosphate can come from many of the same places the nitrates come from, mainly from fertilizers and from animal wastes, along with wastewater treatment facilities. While dissolved oxygen, nitrates, and phosphates are all chemical measures of water, E. coli is actually a biological measure. Because E. coli is a living bacteria, E. coli is commonly referred to as an indicator organism, because while E. coli alone generally isn't dangerous, it usually means there are other bacteria present that are dangerous. If it is ingested, it will probably make you sick. Poorly operated septic systems and wastewater treatment facilities are often to blame for E. coli pollution. E. coli is tested for by spreading a sample water over a growth plate, which will cause the E. coli to grow and become visible to the naked eye. Shown here is an E. coli test plate example. Each dot represents a bacteria colony, and the grid makes it easier to count and easier to get a better picture of how much E. coli is in your water. As it has been discussed thoroughly throughout this presentation, temperature is very important and can affect a lot of things. The rates of biological and chemical processes depend on temperature. For example, the dissolved oxygen level depends on temperature, rate of photosynthesis, metabolic rates, and even sensitivity to diseases, parasites, and toxins. The normal range of temperature is about 5 to 35 degrees Celsius and can vary a lot depending where you are geographically. Aquatic organisms, from microbes to fish, are dependent on certain temperature ranges for their optimal health. Optimal temperatures for fish depend on the species. Some survive best in cold water, like the salmon and trout mentioned earlier, whereas others prefer warm water. If temperatures are outside this optimal range for a prolonged period of time, fish can get very stressed and even die. Cooling water discharge is one of the major causes of temperature change. Also, urban stormwater runoff, removal of shading streambank vegetation, and groundwater inflows. Removing shade from the edgewaters can also have an increase on temperature. Groundwater, on the other hand, can cause a decrease in water temperature, which can be equally as dangerous. So what does all this have to do with fish kills? Well, first, let's start by discussing the basics of a fish kill. A fish kill can be defined as a localized die-off of a fish population, usually due to human pollution. Fish kills can vary in magnitude depending on how bad that pollution is. One example, shown below, of a rather large fish kill happened recently in April 2012. On the eastern branch of the Rocky River, located right outside Cleveland in northern Ohio, an estimated 31,000 fish were found dead. The cause of this fish kill was found to be an illegal dumping of liquid cyanide into a storm drain. Cyanide is used in precious metal production and is highly toxic. So, what else causes fish kills? Well, pretty much everything we've already discussed. From a high or low pH to excessive or sudden temperature changes, to low oxygen levels or a discharge of toxins such as liquid cyanide. Fish kills are often the first visible signs of environmental stress. The investigation of fish kills is taken very seriously and is often done very urgently by environmental agencies. Water quality testing parameters, like the ones discussed above, can be useful in determining the causes of a fish kill, if the tests are run during or immediately after the kill. That is why a sense of urgency is very important with these matters. A fish kill often occurs downstream of the pollution source. So how do we quantify how good our water is based on the parameters that we just learned how to test for? Well, one way to do this is the Water Quality Index. It's a measure of how polluted a body of water actually is. Now, I can take many different parameters into consideration, but 6 is usually the minimum, and usually what we use to calculate the WQI. The WQI utilizes a weighting factor to differentiate between important parameters and less important parameters. For example, DO is a very important parameter, so it's going to have a high weight in this calculation. Q values are also utilized, and they are numbers that are given in a table and correlate to the level of each parameter to characterize each on a scale of 0 to 100. We'll explain that further in a second. So, we can go from our test results to get a Q value, then we multiply this Q value by that weighting factor, and we add all your subtotals, and you'll get a grade, a percentage out of 100, just like you do in school. So, if we have this here example with dissolved oxygen, nitrate, phosphate, and pH, we can find how healthy this water actually is based on the weighting factors and the tested value. So we go to our Q value chart for dissolved oxygen. The percent saturation was 90. So we look on this chart on the left here, find 90 in the percent saturation column. It corresponds to a Q value of 95. That's an A, that's really good. So we can go over to our chart, put a 95 in our Q value section, and then we want to multiply that by the weighting factor. We get 28.5. Now, when all these are added up in the end, we'll get a grade out of 100. So 28.5 is the contribution from dissolved oxygen. Nitrate, which was measured to be 1.75, isn't found on this table, but 1.5 and 2 is. So we can go halfway in between that and do what's known as interpolation. So halfway between 92 and 90 is 91. So we're going to have to mark down 91 in the Q value column for nitrate. Multiply that by our weighting factor, we get 18.2 as our calculation. Next is phosphate. We measured that to be 0.3 milligrams per liter. So we look that up on our chart to the left, and we can see that our Q value is 90. So now we're going to want to write down the Q value in our chart, 90. Then we multiply that again by our weighting factor, which is 0.2 in this case, to get 18. The next value that we want to find the Q value of is pH. As we can see, the tested value is 6.7. So we look on our Q value chart, and it seems we only have 6 to 7. Now we're going to need to interpolate to find the Q value associated with 6.7. This could be a little tricky. So we have this to make it a little easier. As you can see, this pH of 6 to 7 correlates between a Q value of 55 to 90. So if we go halfway in between that at 6.5, we can go halfway in between 55 and 90 to get 72.5. So we want 6.7, which is just about halfway in between 6.5 and 7. We can see that it's 81.25, but we want 6.7, not 6.75, so we'll just go a little bit less than 81.25 and round it to 81. So we put 81 in our Q value section of our chart, multiply it by our weighting factor to get 24.3. Then, if we add all our calculations up, we can get our water quality index, which is a grade out of 100. And as you can see, an 89, that's a B+. That's pretty good water there. Just like in a classroom, excellent is the A range, 90 to 100. Good water, like what we just had, is 70 to 90%. Medium, 50 to 70. Bad, 25 to 50. And very bad, 0 to 25%. And that is the water quality index. The water quality index is a good indicator of overall stream health. We have to remember, it's our job to preserve nature's waterways so that they can be enjoyed for years to come. Now with the information presented here, hopefully it will be easier for you to see how interconnected everything actually is, and how one little thing can have a huge impact on the environment. It's also important for us to see just how everything works, so we can tackle any environmental issues, or any issues for that matter, efficiently and effectively. Pollution is not a problem of the individual cities or states, it's a problem of the entire watersheds. So if we can get beyond these political boundaries and work together as one watershed, we can keep our environment clean, and we will be doing a great service to everyone around us. Thanks for sticking with us through this video. Hope you learned something.